Okay, this is problem 4 from the fall 2010 exam. It says two infinite sheets of charge are in the YZ plane, one positioned at x equals 4 centimeters and the other at x equals -1. The two sheets have charge densities shown. So we have a negatively charged sheet here at x equals 4 centimeters and a positively charged sheet here at x equals -1 centimeters. And we need to calculate the electric field at point A. So here, between the two plates. So the electric field at this point will be the electric field due to this plate plus the electric field due to this plate. So we know that it will point away from this positive plate. It'll point toward this negative plate. And those two contributions will add. We'll get an electric field pointing in the positive x direction between the two plates. Okay, so the electric field at this point, so E at A, is the electric field at A from the positive sheet plus the electric field at A from the negative sheet. The electric field from the positive sheet is the positive charge density over epsilon naught, and so that's independent of distance, plus the negative charge density over epsilon naught. So both of these will add in the positive x direction. So this is equal to, the positive charge density is 30 nanocoulombs per meter squared over epsilon naught, and then plus this negative charge density. So I've kind of incorporated this negative sign into and the directional vector. So this is just going to add, so plus 20 nanocoulombs per meter squared over epsilon naught. And so we'll get something that's 50 nanocoulombs per meter squared over epsilon naught, and whatever that is, that will be in units of volts per meter or newtons per coulomb, and the direction's in the positive x direction. What is the minimum work that you must do to move a 20 microcoulomb particle from point A to point B? Okay, so we're going to move a particle from here to here. Since the electric field only points in this direction and is a constant, then moving in this direction, it doesn't matter how far we move in the y direction, since moving in that direction will always be perpendicular to the field. So we just need to know the x component of the displacement from A to B. And so that's 2 centimeters. We're going to move 2 centimeters with the field. So we're going to do negative work moving with the field. So the work is the charge times the potential difference, which is just the charge times the electric field times the distance moved. So we found the electric field in this part, the charge is given to us, so 20 microcoulombs times 50 nanocoulombs per meter squared over epsilon naught, whatever that was, and the distance was 2 centimeters times 0.02 meters. So whatever this comes out to will be the work, and that will be something in joules. Okay, part C is calculate the electric potential difference between VD minus VC between the points D and C as shown in the figure. So points D and C were here and here. So the electric potential difference is the amount of work it would take to move a positive charge from one of these points to the other. So we're moving VD minus VC. That means that the final point is D, the initial point is C. So we're going to move from C to D. So the work done is the charge. So the work per charge that we're doing is the potential difference. So if we're going from so C to D, then the work done in going from C to D per charge is the potential difference. And so there are three parts of this. We're moving, we have some constant electric field out here, some constant electric field in between the plates, and some constant electric field out here. So let's first calculate the fields, and then we'll know how far we move in this field out to the left of the plates, how far we move in this field in between the plates, and then how far we move on this other side of the plates. So out here, we're our electric field from the positive plate points in the negative x direction. So this is E positive, and due to the negative plate points in that direction. So these will cancel partially out here. And here they both pointed in the same direction, and in here they will both they'll cancel again, but E positive will point in that direction, E negative points in that direction. So out here the net direction is or the net field will point in this direction and will be 30 minus 20 nanocoulombs per meter squared. So it'll be 10 nanocoulombs per meter squared over epsilon naught, and that will be in this direction. So in the negative x direction. Out here, it'll be the same magnitude, but in the opposite direction. So 10 nanocoulombs per meter squared over epsilon naught in the plus x direction. So it's the force due to this positive plate is stronger than due to the negative plate and points away from the positive plate, so that's why it's in that direction. And in here we already found was 50 nanocoulombs per meter squared over epsilon naught in the plus x direction. Okay, so now we know our electric field everywhere, and so to calculate the potential difference, we need to move through this field for 1 centimeter in the x direction, through this center, the field between the plates for 5 centimeters, and between on this side of the plates for 2 centimeters in this field. So in this first part, we're going to be moving in the positive x direction, and the electric field was in the negative x direction. So we need to apply a force to counter the electric field. So we're applying a force in the positive x direction and moving in the positive x direction. So the electric field times distance is going to give us a positive amount of work done for that first part of the when we're on the left side of the plate. So that's 10 nanocoulombs per meter squared over epsilon naught times 1 centimeter, or times 0.01 meters. So this was a positive number. Then when we're in between these two plates, we need the electric field points in the positive x direction, so we need to apply a force in the negative x direction, and we're moving in the positive x. So now in this area our work will be negative and going from here to here. So we have a negative, so we're going to subtract energy. We have negative 50 nanocoulombs per meter squared over epsilon naught, and that's plus 0.05 meters in that direction. And then for this last part out here, we're going to move in the positive direction still, and our electric field is in the positive direction. So electric field points that way, the displacement field vector points that way. Our force counters the electric field and is this way. So our force is in the opposite direction that we're moving. We'll do some negative work. So this will subtract off 10 nanocoulombs per meter squared over epsilon naught times this distance out here, so 2 centimeters times 0.02 meters. And so whatever this adds up to, so this part here, we moved half the distance as we did out here, so this will cancel half of this part, and we're going to end up getting, well, I need a calculator, but we'll get the solutions are online, so you'll get some value, and that will be in volts when you multiply these out. Okay, and plot the electric potential as a function of position along the dotted line in the figure on the previous page. The electric potential of the right plate is defined to be 0. So the electric potential at here is 0. So if you imagine moving toward it on this side, out here moving toward these 2 plates, our work was positive, since we needed to apply a force to counter the field, which was in this direction. So our force was in the direction we were going as we're coming in this way. So we're doing positive work out here, negative work in here, and we'll get to 0. And then on the other side, we were doing more negative work. So at x equals 4, we have a 0 potential here. On the left-hand side, our potential will drop linearly. We have a constant electric field. Between the plates, it will also drop, but we had a larger field inside the plates, so actually we'll have a this should be sharper than this one. So in between these 2 plates, our potential decreases linearly with some large slope, and then out here it has, let's see, a 1/10 of the field strength, so a 1/5 of the field strength, so it should have a 1/5 of the slope. And then out here, we had, we did positive work to get from here to here. So I was like pushing it up a hill with this low slope here. So we will have something like this.